بسم الله الرحمن الرحيم. معكم دكتور مدحت فهمي، كلية الهندسة، جامعة وادي النيل، متعاون مع جامعة مروي التكنولوجية عبد اللطيف الحمد. وإن شاء الله هندرس مع بعض أو هنشتغل مع بعض مقرر ميكانيكا المواد، وهو عبارة عن مقرر يختص بطلاب الماجستير للهندسة الميكانيكية. طيب، هنتناول إن شاء الله من البداية كده نعرف بالمقرر والأبواب اللي هيتضمنها مقررنا. المقرر حقيقة يضم about 3 chapters. First of all, we have theory of elasticity, and this chapter contains boundary condition and some other subjects as surface force and stress function up to formulation of elastic problem. The second chapter contains plates, and in plates we are going to discuss linear analysis of rectangular and circular plates. The third chapters contain experimental stress analysis techniques, general knowledge of strain gauge and photoelastic and brittle coating, dynamic relaxation methods, and for plates. Second, we can discuss some of the references which has now appearing on the screen. These references contains many of the subjects in our program. Some of them can be reached from the net as software, and others we have these notes. It can be also as a reference for this subject. Let us start today with the first chapter, and it's called strain energy method. If we talk about strain energy method, it means that the energy is stored inside a part according to forces exerted to it. That means this energy produced or we obtain it from the other forces outside. So if we look here for the wear done مثلا, if we have a force and distant about x meters or s somewhere, in this is as a wear done for a path. Also, if we talk about the wear done which is happen according to forces related outside a body or an element, it has to be have Fs, which is called which is about the half distance of the wear done, and this we can integrate it to obtain the strain force. So if we talk about strain energy, the strain energy, it means half multiplied by the force multiplied by the distance. It is about to be half bx, and we know that sigma is equal to b divided by x, so is b equal sigma a. And if we also go to the strain equal the تغير, we mean التغير في الطول divided by the original length. That means التغير في الطول أو إذا كان extension or تغلص يعني معناها we mean we have x equal to epsilon L. If you put this epsilon in related to sigma divided by E, which E is modulus of elasticity, so X equals sigma divided by EL. That means we can get the strain energy, which is mentioned as U, or capital U, it is sigma square V divided by 2E. If we take this for a body, as we seen here in the drawing above the page, if we take about an area at a distance y from the neutral axis xx, and this area we put it as delta x, and we take this element from a main bar, it has a bending moment in the two directions. If we relate it to the sigma over y equal m over I, which is the bending moment formula, we can put sigma equal to m over I y. And this, if we make delta u, we have integration m square y square divided by 2e I square multiplied by a delta x, which is mean المساحة الarea. Because we put as the first sigma خدناها في موضع القانون، وبالتالي anything not related to integration we can put it outside, we reach to this equation. But in this integration of ay square is equal to I, which is the second moment of area. If we put it in the previous equation, we can reach to this equation, and if we integrate it to the actual distance or actual areas, we reach with a formula that is mean u equal to integration of m square dx divided by 2ei, where m square it is the moment and x is limited from the length of the beam. Here we get a new theory. It is called Castiglione theory. Castiglione theory is one of the theories which can used to calculate the deflection and the slope of the different beams. It is similar to virtual work, similar to Macaulay methods and others. لكن it is easier to use. There is if we here if we take an element, big element has for example many forces exerted on it, say as in the drawing here, b1 b2 b3 up to bn, where is bn it is a number of the forces. If each force of this it has a function about مثلا يعني تدينا about delta 1 delta 2 delta 3 وهكذا، يعني احصل extension according to the force if it is extension or compression force. So we can put u general, it is half b1 delta 1 plus half b2 delta 2 up to half bn delta n. From this formula we can reach that the strain energy it can be u plus a partial of جزء not a partial, sorry, it is partial or a little amount of strain energy. And also we can say that delta n equal to partial u by partial bn, what is n it can be from 1 up to infinity. If we want to discuss this through examples, say for beginning we can take example 1 to be solved. So here he said find the deflection at the free end. The free end it means the position where B is acting. So here we have a built-in beam in one side, in others they can say it's Kabuli. This we have one force B acting on the free end, and the length of the beam it's equal to L. So the answer can be u from the previous equation we get it equal integration of m squared 2ei dx. And also 1 over 2ei, it is, we can put it out of integration. We have inside integration only m squared dx. We began this example from the scratch so as to, in the other examples, we can begin writing the formula directly. So if we make partial u by partial b, we get v, which is the deflection. It means in Arabic الانحراف. So partial, we are going to make partial u for this equation by partial b. It will be طبعا 2 في m بعد ذاك partial m by partial e, 2 is off. So we get this equation 1 over ei integration m partial m by partial b dx. If we relate also to this drawing, so we can get m. When m is this, we mean it is a bending moment. So it is equal to minus b multiplied by x, and a minus because it is applied from the upside to from up to down. If we make partial m by partial b for this moment, we get minus x. So if we put this in the formula of v, which is this formula, so we get an equation b ei integration from L to 0, from the total length of the beam to x, this according to the x-axis. So inside we have x squared dx, which is begun to become x cubed by 3 وهنعوض من L ل 0. We get that means v equal to b L cubed على أو divided by 3ei. Here this means that the deflection at the free end for this beam equal to this amount, and it is depend on the amount, هي قيمة أو amount of الforce. If we take another example, but the same one, but we have forces exerted in the middle span. قال find the deflection at the free end. هو عاوز الديفليكشن في الفري end هنا أو الطرف الحر. لكن عندنا forces واحدة exerted in the middle. That means the length of the beam L divided by L over 2 L over 2. So in this case we have to put a dummy force. That dummy force we call it Q, for example. That means Q equals 0. بمعنى أنه هو حمل وهمي. هنا خدناه عشان نتعامل معاه في الحتة دي. ودي لأنها it is divided, we can divide it in two sections. كويس. According to that mean V equal partial U by partial B, واللي هي نحن حصلنا لها في المعادلة في المثال السابق 1 divided by EI. هيبقى الانتجريشن بتاع الجزء الأول from L على 2 to 0. كويس. وداخل الانتجريشن M1 partial M1 by partial Q بيعمل by partial شنو؟ by partial Q لأنه ده الحتة اللي احنا عاوزين فيها الديفليكشن dx. الجزء الثاني هيبقى لنا 1 على EI أيضا integration from L to L على 2 بالنسبة ل M2 و M2 دلالة للبندing in the second section. And so partial M2 by partial Q dx. Let us first we have to put the value of M1, that is means the moment in the first section, it is minus QX. Where is X? It is greater or equal 0, less than or equal L divided by 2. بنجيب أيضا partial M1 by partial Q بقت ناقص X. نجيب العزم أيضا في السكند section, so it is ناقص QX أيضا لأنها exerted from the top. ناقص bx ناقص b multiplied في الديستنت. نحن بنتكلم عن عزم لأن الفورس المومنت it is a force multiplied by distance. so it is become x ناقص l divided by 2. وهنا x الحالة دي اللي هي limited بين l over 2 up to l. So if we rearrange this equation, we reach this one. So if we make partial m2 by partial q equal to ناقص x. Let us نعوض كل الكلام ده في المعادلة بتاعت ال v الأولى، نحصل على معادلة جديدة. وهذه المعادلة الجديدة نحن لا ننسى أنه q equal to 0. So it is equal to 0. Any part of this equation will q inside is going to be 0. So we reach with this equation, and also we have to integrate it, the two sides of the equation زي ما قلنا. وفي at the end we reach about bl تكعيب over ei 7 على 24 ناقص 3 على 16. دي لو وحدنا الكسور الموجودة هنا we reach us 5 over 48 bl تكعيب divided by ei. ناخد خلينا ناخد مثال آخر another example. لكن at this time we have instead of concentrated load as the two previous example, we are going to take a distributed load. Distributed load on beam built in one side beam. It has a length about L and distributed load equal to W. قال find the deflection at the free end. أيضا عاوزه في الطرف الحر. بنفس المستوى معناه ان احنا هنفرض انه عندنا دمي فورس، والمره دي هنفرض الدمي فورس بتاعتنا سميناها بي. كويس؟ وبنرسمها دايما لو لاحظت في المثال ده والمثال اللي قبله انه عباره عن سهم من اعلى لكن متقطع. المعادله بتاعتنا لانها من قطاع واحد هيكون عندنا طرف واحد للمعادله اللي هو في بيساوي لنا بارشيل يو باي بارشيل بي، لانه احنا الحمل اللي عايزين عنده الانحراف اللي هو بي. في المره اللي فاتت كان مثلا كيو، وبتبقى لنا اللي هي 1 على اي اي. التكامل بتاعنا هيبقى من ال ل 0 ام بارشل ام باي بارشل بي دي اكس. بنجيب ام لمقطع هذه العارضه انكلودد البي فورس اللي هي الدمي فورس ذاتها، ونجيب لها بارشل ام باي بارشل بي، ونجي نشيلهم بعد ذاك نعوضهم في المعادله بتاعت البي. بعد ذاك عندنا بي اساسا هي وهميه اذا ايكوال تو 0، نجي ناخدها تبقى الحدود بتاعتها 0. بعد ذاك نجي نعمل التكامل ونعوض الحدود بتاعتنا للتكامل من L to 0 ونحصل على المعادله النهائيه اللي هي WL raised to 4 divided by 8 EI. If we take another example, this time we are going to calculate the slope. In the first 3 examples we calculate the deflection. نحن here we are going to calculate the slope. It mean الميل يعني بتاع العارضة. we mean that here we have a beam برضو built-in beam has a force equal B at the free end. To calculate the slope we are going to put here a dummy moment. dummy moment اللي هي عبارة عن كيرف أيضا متقطع في سهم في شكل كيرف متقطع سميناه بي دوت. طيب سيتا اللي هي in answer here equal to dv by dx اللي هي عبارة عن تفاضل شنو؟ عبارة عن تكامل الانحراف. وإذا سيتا معناها equal نفس المعادلة بتاعت الانحراف اللي هي هتبقى لنا لكن بالنسبة لشنو؟ بالنسبة لسيتا اللي هي 1 على اي اي integration from L to 0 m partial m by partial m dot دي اللي هي نحن الحمل او سموه شنو العزم الوهمي دي اكس. بنوجد m طبعا ايضا العارضه دي مكون من قطاع واحد اذا عندنا m وحدي وبنجيب لها partial m by partial o ولقيناها ناقص 1. بنرجع نعوض الكلام ده في سيتا وناخد الحدود بتاعتنا ناخد التكامل بتاعنا. ولكن لانه عندنا نحن نجيبيل ام دوت دي فرضناها بتساوي 0 نجي ناخدها 0 اي جزء فيه ام نوت من الحدود بتاعت المعادله بتاعت الايكويشن ايكوال تو 0 نحصل على انه سيتا نحصل عليها هذه المعادلة، نعمل لها التكامل من L ل 0، نحصل على أنه B اللي هو الميل at the free end أو السلوب at the free end BL square divided by 2E. In equation 5, in example 5, we have this time simple support beam. This simple support beam, it is has one exerted force is the middle, so that the length of the beam, it is L, we divided L over 2. Here also he want to find the mid-span deflection. He mean that he want to calculate the deflection at the mid of the beam. So we put the previous equation about V. Lakin in this time we have divided the beam in two sections, so we have M1 and M2. We have to calculate M1 and also reduce partial M1 by partial B و M2 وأيضا نحصل على partial M2 by partial B ونعوض دول كلهم in the equation of the deflection. So we get this equation. Here we have no dummy activity because we have a force exerted in the mid of span as the example, and so there is no need for the dummy activity. So from the calculation and the limit of integration, we reach about BL cubed divided by 48 EI. If we لو انتقلنا إلى example ثاني it is called here example 6, we قال here find the reaction, أوجد الرياكشن، وهنا في drawings it's R. It is also built-in beam in one side, has a forces in the middle equal to B. As the same here, if we return to the drawing of the beam, it can be divided into sections. So we are going to have M1 and M2. So we divide the equation of deflection into two pieces, M1 and M2. For M1 we reduce partial M1 by partial R, and also in the second we reduce partial M2 by partial R. We reduce all of this in the formula equation اللي هي for the deflection V. لكن here we want the amount of the reaction R, and R here it is a force أو رد فعل يعني للforces الموجودة. And where is the reaction in a beam? That means in this point there is no deflection, so V equal to 0. from V equal to 0 لو خدتنا الطرف الأيسر اللي هو V equal to 0 وباقي المعادلة، بالتالي ممكن نتحصل على قيمة R. طبعا ده بعد إجراء التكامل، واللي هو نحن هنكامل برضو العارضة مقسومة لقسمين من L إلى 2 إلى 0 من L إلى L إلى 2. بناخد دائما القيمة القصوى to get a positive answer. So we reach R equal to B over 8. After this we have many problems. I need you to try to answer it, and there is answer after each problem, and we have up to 12 problems. Okay. طيب، أتمنى التوفيق، والسلام عليكم ورحمة الله تعالى وبركاته.